Okay, we're looking at some trig tips, and hopefully these will be really handy for you. Some by hand methods in this one. So this video should be watched straight after the previous one, which was the tech one. It was tech number 2, and it involved using Desmos and Excel. Okay, there's been 2 of those recently, and it's the most recent one because it actually uses data from that. So go and watch that if you haven't watched it. Don't watch this, watch that first, then come back to this. Okay, some of the things we've been learning lately, just summarized here. So whether it's A sine B x plus C plus D or the cosine equivalent, we've got the amplitude is the magnitude of A, so that's to do with the vertical stretch. There's another way of thinking about A too. Not only is it the amplitude or the vertical dilation from your standard graph, it's a bit like saying on average it's how far the peaks and troughs are away from the mean. So it's the peaks and troughs, the high and the low points, how far from the average point. And this average of the graph is something we'll talk a bit more about when we get down here in a moment. So it's good that we can think of things in different ways. What we've seen before too is that depending on if you're working in radians, the period is 2 pi divided by the parameter b. If we're working in degrees, the period is 360 divided by b. So it depends which angular measure you're working in. We've got C is the phase shift, and we know that's in the horizontal direction. So if we have x plus C in the brackets, alright, that will move its C units to the left, and if we have x minus C, it'll move C units to the right. The horizontal phase shift, or the horizontal translation. And the average is D. D is the vertical translation, but compared to the base function, but it's also the average value of the function. It's the average value of y. So it's the average vertical value. Okay, so for something very rough like this, if we have a graph sitting on that, like that, something like this might be the average. There's just as much above as below. And whatever that y value is there, that would be the value of D. So maybe you can see how that links to its other way of thinking. The other way of thinking about it is you might be able to see how that links to vertical translation. Similar idea. So average y value is D. We're going to use all that now in conjunction with what we saw in that previous video. That's why you must watch it first. And what we've got is the data and a few screenshots from that previous video. The previous video, you might recall, was we were actually working in degrees, but this process is pretty much the same if you're working in radians. And we got our data, and it was a tidal creek, and at various points in times it has different depths. It has highs and lows, and this creek goes up and goes down. So basically we used tech, and we used regression. You can see the tilde there, and we chose to use sine, and that's what we got. And you can see the screenshot with my blue writing there and part of the graph and so on. We're going to see if we can use by hand methods to come up with an equivalent formula. Now it's unlikely to look exactly the same as that one, but we want to compare it because this is a by hand technique video. Now we're going to work on D first. I think that's an easy one to work on. So we're going to see what we can do, see if what we get matches that, and discuss why it might be different. So the D, as we just said a second ago, it's the mean or the average of all the y values. So to get an average, we sum all the values up and we divide by the number of values there are. Now, of course, y values means y-axis. We've actually, from the previous video, you saw that we actually plotted depth on the y-axis. So we just need to add all these d values up, because that's the equivalent to the dependent variable, okay, the y. So these ones in the second column here all need to be added up, and you would show that normally by adding them together and divide by how many. And basically I've done the adding just to save time on the video, and I got 15.35. You might be able to check my calculations and let me know if I've made any errors there. But 15.35, and there's 11 data values is what I get, and from that I get, if I round that, I'm probably a bit naughty rounding it to 3 decimal places when there's only 2 up there, but anyway, 1.395, and that's our D value we get by doing that. And notice how it's 1.352 back up here, so that's pretty close. Next one, which might be fairly easy to pick off, is A. Now A is the average basically of the distances that the peaks and troughs are away from the mean value. So it's the averages of the distances. So it should have of the in there, because if we look back up the top, earlier we wrote that A considers the peaks and troughs and how far from the average point on average it is, so how far the peaks and troughs are. So we're looking at that distance there, which should be the same as that distance there if it was a pure sine function. This one's made, you know, it's a model, it's made from a natural thing, so we might get some fluctuations, alright, because, you know, nature doesn't follow a mathematical function perfectly. We just got to make our model useful and do the best we can. Okay, so that's there. That's basically how we manifest A, that distance there, which hopefully is the same as that, and that all very close. Anyway, with our real life data, it will fluctuate a bit. These will vary a little bit each as we go along, but if we average them out, we should get something reasonable. Let's check it out. From the step above, our average was 1.395. Okay, that's it there. The thing is, when we look at the data, some of the data is the peaks and the trough from, again, we're reading from column D, it's the depths. Some of them are above 1.395, like this one. Some of them are below. It's like half and half. So we don't want to get negatives, we want the pure distance. So we will put the larger of the numbers first, is one way of doing that. If you've learned absolute value before, which you might not have, you could use that instead. But we're just going to put the largest number first. So I'm going to show you the partial calculation. So for the first depth was 2.11 meters. I'm going to take that 1.395 off. And then I'm going to add it to, we've got the next one, which was 0.77. Now I'm going to put that second because it's smaller than the 1.395. That way you're going to get positive distances away, which you need. The third one, 1.92, and basically that's bigger than 1.395, and you just keep repeating that. You would then add the next one, you'll get 11 of them. Alright, so we're adding down the list there. Okay, well, and you can see the last one I got to there was 1.92, so I got that far down. You'd continue down the list and basically add them all together. Then you get a total, and then you divide that total by 11. Now when I got the total, please let me know if I've made a mistake, but I got 7.89 45, etc. So basically we need to divide that by 11 because it's just like there we're finding the average. So if you go 7.89 So the average is 7.89 divided by 11, and we get 0.717. Somebody in here is singing. So 7.17 if we find the average. Okay, and basically that compares reasonably with that. There is a bit of variation there, so you might want to talk about why that is. Perhaps with tides there's something about the peaks and the troughs that's not consistent that you could talk about. Okay, so there's a difference between that average method and this regression method. It's not hugely different, but it is a little bit different. In our next video we're going to continue on with this, and we're going to look at C and B, and then basically we'll be finished. So tune in for the next video.